好，那么接下来我们开始下一个 session，就是由日立的松本周平从日本专程过来，我们做这样一个分享，就是关于SPDK 里面的 data protection 的一个分享。
你好，我叫周平松树，我好高兴再来这里。今天我讲话 in the protection with SPDK for NVMe TCP target. That's all from me about Chinese speaking. So let's start my presentation. Now I'm serving one of SPDK co-maintainers and developing and maintaining SPDK, and I'm also working for Hitachi and to facilitate open source and SPDK adoption in our company. And this is the agenda of my talk today. The first, I think data protection may not be familiar for everyone, so I want to have some brief introduction about data protection, and then I want to speak about some detail about new feature about the diff support in SPDK and TCP target, and I want to share the result of initial performance evaluation next, and I will close my talk by summary and next step. So data corruption refers any data error which occur during reading, writing, storing, transmitting, and processing, and which cause unintended changes to its original data. And when data corruption occurs, the file containing the corrupted data will cause unintended results when accessed. Data corruption can occur anywhere, and there are several reasons of data corruption: software errors, hardware errors, human errors, or firm errors. And there are two types of data corruption. One is detected data corruption, and another is silent data corruption. Detected data corruption can be fixed by correcting the corruption, but undetected silent data corruption have no indication of error, and so which occurs unintended result when accessed. So silent data corruption is very dangerous and should be avoided, but individual data protection mechanisms don't span among layers. So when data corruption occurs between layers, individual protection cannot prevent such type of error. So end-to-end data protection is critically important for storage application. And data integrity field, this is standardized in the end-to-end data protection, and so this is very popular and among from long ago. So we decided to use SPDK, diff for SPDK. And how to use diff is, at first, application creates diff at data creation, and intermediate layers can check diff when data is transferred on them, and target device can have data and diff and do final check before storing them into storage media. And diff is made of 8-byte field and has 3 fields. One is guard tag, which contains checksum and can detect data error. The second one is application tag, and how to use is up to the application. And the third one is reference tag, and this normally contains the lower 4 bytes of the block address, and which can detect wrong destination of write and read I/O. And especially for NVMe, there are many variables about diff configuration. So we introduced diff library to use the feature easily. And this page shows the use case of diff. So traditionally, for storage arrays, dealing data corruption is critically important, and returning no data is better than returning wrong data. And so storage arrays have used this extensively. And for some hosts that are not aware of diff, so front-end I/O card have inserted diff and stripped diff for read and write I/O. And for some hosts that are aware of diff, for example, Oracle database or something like that, already recognize diff, and so hardware I/O card just pass data with diff for read and write I/O. And traditionally, such diff features were achieved by utilizing hardware feature, but I think it will be nice if we can provide such features without using any specialized hardware. So we started to work on software-defined diff feature almost 1 year ago. And in April, so SPDK 19.4 support 2 diff features. First, the first one is iSCSI tag. So one of our use case requires to have diff insert and strip feature first. So I provided this feature, and then next I supported diff pass-through feature in SPDK NVMe Fabrics target. And then next, this is the latest version of SPDK. SPDK 19.07 support newly diff insert and strip feature for SPDK NVMe Fabrics target. And then, some use case will have stackable virtual devices. So when we use stackable virtual devices, destination block address will be changed among intermediate storage layers. So we have to support remap reference tag. Without remapping, diff check will detect wrong destination. So we have to support remapping feature. So as a sample implementation, we provided initial support for such remapping feature for some of SPDK stackable virtual devices. And the final one is, this is very popular for initiator side. So some application can process data and metadata if they are separated. So that is called DIX. But on the target side, some storage application may be helpful if SPDK supports separate metadata. So we also provided initial support for separate data and metadata. So we will integrate this separate metadata with this diff insert and strip feature in near future. And from next, I will explain some detail about the latest addition about the feature for over fabric target. So this is the key idea to achieve comparable and enough performance when we enable this insert and strip feature. So we want to avoid extra dead copy or any bounce buffer. So we have created special scatter gather list. So for write I/O, by creating special scatter gather list, we will leave metadata space for each data block, and then when we read data block from host to target, we leave each metadata space and fill if data after leaving space. On the other hand, for read I/O, this type of data is stored in the storage media, so we do completely opposite operation. So also we create special scatter gather list, and at this time we will use this list as a gather list, so we ignore these metadata spaces, and only data block, we transfer only data block to the initiator or host. So this is a key mechanism how we achieve the software-defined diff insert and strip feature. And so the key idea is same between iSCSI and NVMe, but plots, we saw some critical differences between them, and I list two major ones. The first one is for iSCSI target, we can limit maximum I/O size by BPD block limit, but this feature is optional, so we don't know the we can't limit the maximum I/O size upfront, so we can't gather all incoming data before submitting to the BDM layer. On the other hand, NVMe protocol has a parameter maximum data transfer size, and this parameter is mandatory, so we can limit the maximum I/O size, and then the target can gather all incoming data before submitting to I/O to the BDM layer. And the next difference is supported diff mode. So iSCSI target only local mode. So iSCSI target only supports diff, instant, and strip mode, but NVMe Flex target supported end-to-end mode first, and then next version local mode. So NVMe Fabric target has to support both mode, local mode and diff mode. So so we see these two major differences. So design and implementation is different between iSCSI and NVMe over fabrics. So from this page, I will explain the difference between iSCSI and NVMe fabrics, and these two pages don't include any about the feature. So I will explain the basic of I/O flow and request structure first. So when initiator sends SCSI write to target, SPDK iSCSI target creates the primary request structure, and then SPDK iSCSI target replies to ready to transfer to initiator, and then initiator sends actual fast data. When iSCSI target receives this data, SPDK iSCSI target creates sub request, and then the target cannot keep gathering data. So at this time, SPDK target submits splitted fast I/O to the SCSI controller. Then target requests the next split I/O to initiator. Then when the target receives the second and final data, the target submits the second and final I/O to the backend SCSI controller. So when the I/O is split into some sub requests, the I/O request structure is like this one. And when the target receives the compression of the first I/O, the target frees the first sub-request, and then the target receives second complete I/O, frees the second sub-request, and then sends the SCSI response corresponding to this SCSI command, and then frees all requests. But overflex target is slightly different about I/O flow and structure. Let me explain this. So the initiator sends out, this is NVMe write one is almost the same as SCSI write. So the target receives, when target receives the NVMe write, so the target allocates request, and so for this case, the target knows the total size of metadata and can allocate all the total buffers or the payload, and then the target send request to initiator to send the first split I/O. When the target receives the first data, the target keep gathering the payload and without submitting I/O to its backend. And then when the target receives the whole payload, the target submits one I/O to its backend. And when the target receives the compression of this I/O, the target sends the response to the initiator and frees the request and this whole structure. So the flow is a little simpler. NVMe TCP's I/O flow and structure is a little simpler than iSCSI, but SPDK NVMe TCP target has complexity in different structures. So I/O flow is simple, but scatter list management is more complex than iSCSI target. I will explain why this complexity is needed. So when the target knows the total I/O size, the target can allocate the total buffers, and the target can create scatter list to keep the location of the buffers. But for some cases, this payload has to be split into some smaller pieces, and each small piece is made of dead PDU, but between NVMe request and the data PDU, there is no requirement about the boundaries. So data PDU will have any boundaries. So we have to have its own scatter list to store that PDU, and that PDU is conveyed by TCP IP packets, and there is no boundary requirement between that PDU and TCP IP packets. So we have to have another separated scatter gather list. So we have to manage 3 levels of scatter gather list, and this is a no. So and if so, this case is doesn't include any diff feature, but we have to add diff insert and strip into these 3 level scatter gather lists. So implementation is slightly complex, but fortunately we could do that. So this page shows the 3-level scatter gather list when diff insert or strip is enabled. So diff, as I said in the last page, diff insert and strip is down the bottom layer. So when TCP IP stack reads data, it leaves diff space into each data block, and on the other hand, TCP stack removes diff space from each data block when writing data to the initiator. But we have to leave diff space all 3 levels of scatter list. So when we create this top level scatter list, we have to leave this space for each block, and then also we have to keep this space on the next level, and so we have to strip or insert diff space for the bottom layer too. So as I said, scatter gather list management is a little complex than SPDK target, but IO flow is much simpler, so that is fine for SPDK. So this page demonstrates or write IO flow with diff insertion. Diff insertion means write IO case. So I highlighted these 3 operations because these 3 operations are specific for diff feature. So when the target read command PDU, and the command is write IO, the target gets diff information from the backend and allocate metadata to leave diff space, and then until reading all data, the target continues this loop, and the target sends ready to transfer PDU to initiator, and then when it receives data from initiator, reading data together with diff insertion. And after completion, this loop processing write IO to the backend, and after completion, created buffer, and then the IO response to the initiator. And the next page shows some slightly detail about this operation. This page also highlights 2 operations because these are specific for diff insert and strip feature. So let's start. This flow also has a loop, and until reading all data for each PDU, the first create a scatter list. This is the bottom scatter list shown in the last page, and read incoming data by TCP IP stack. And by using this special scatter list, diff space is left automatically, and then generate and insert diff into the spaces. This page shows the detail about how to process the split case by using some animation. So incoming write data may be split into multiple TCP packets by any reason. So the target has to adjust scatter list before every read. And the idea how to process this case is, fortunately, checksum, we can split and merge CRC checksum. So if the new read ends in the middle of the data block, so in that case, the target saves the computed interim guard value into some temporary area, and when the target reads the remaining data, the target combines the saved interim data and newly computed data and creates the whole CRC checksum. So I will show by using some simple animation. So first we create the scatter list. So this is made of two data blocks. Oh, sorry. So I tried to I used more dark color, but this is my mistake. So this should be blue, but almost white. So please I apologize for inconvenience, but this shows we tried to read data block 1 and data block 0 and data block 1, but we could read the whole data block 0, but we could read only half of data block 1. In this case, we can compute checksum for data block 1, but the computation of diff value for data block 1 don't complete, so we save the interim checksum value into this temporary area. And then when we try the second read, we will create to read. When we try the second read, we create this category to try to read remaining block 1. And fortunately, in this case, we could read the remaining data block 1. And then so by combining this saved value and newly computed value for this block, and we can get the complete computed value, and we can insert the diff value into this area. And so this page shows the second difference I explained in a few pages ago. So SPDK 19.07 supports two diff modes. One is end-to-end diff mode, and another is local mode. So we want to keep these two modes. And so, but according to this diff mode, we have to control whether diff setting is exposed to initiator. So when we enable diff, end-to-end diff mode, we can expose diff setting to the host or initiator, but when we use enable local diff mode, we can't expose diff setting to the initiator. So NVMe controller has to control whether diff setting is exposed or not. And so, SPDK 90.7, this diff mode setting is per NVMe transport, but we may want to control diff mode setting with finer granularity, for example, per host or per initiator. And this overflow controller is created per initiator or host. So we decided to copy diff mode of transport into NVMe controller at its creation, and so NVMe controller controls whether diff mode is exposed or not by referring saved diff mode. So we will be able to support more finer granular diff feature by utilizing this configuration. So from the next page, I will share our initial performance evaluation. But this performance evaluation is very initial and very simple configuration. I use two Xeon processor servers, and target side, I want to know the exact overhead, so I use single CPU core on the target side, and we haven't tried evaluated VPP performance yet, and at this time I used Linux kernel TCP at stack, and I used one NVMe SSD on the target side, and I needed to use pretty recent NVMe SSD because to use the feature, we need NVMe SSD needs to have scatter gather list feature. So some old NVMe SSD only supports simple partition, so they don't support scatter gather list. So I needed to prepare some new NVMe SSD to evaluate performance, and I created. So I partitioned one NVMe SSD into some virtual VDEVs to increase the connection when we evaluated performance. On the other hand, on the target side, I used SPDK TCP initiator, and I used 4 CPU cores on the initiator side, and I used FIO2 and SPDK FIO plugin on a single 10 gig link. And this is a result of 4 KB random read. So this is the baseline performance by using SPDK 90.4, but when we changed to use the latest SPDK, we saw 22% overhead improvement, and this was due to great work by Ziyang. So Ziyang had sessions just before. So this improvement is due to Ziya's great work. And the third one means I changed NVMe format to include metadata, so 512 plus 8, but I enabled only leaving spaces and not filling diff data and not enabling diff check. So just leaving, just creating and removing the space But this case highlights the case when we create special scatter list, and this caused 16% overhead. And the fourth one is the difference from the third one is enable diff check, and this difference added extra 3.5 overhead, and totally we saw about 20% overhead when we enabled this feature. On the other, this page shows the write I/O. So different from read I/O, we don't see any difference between 90.04 and 90.07. And the third one is the same as the last page. So special scatter list added 18% overhead, and diff checks or diff computation added extra 4% overhead. So we saw totally 22% overhead. So this 20% overhead is not so small, but I believe I hope we can find any, but 20% may be acceptable for some use cases, and this is initial performance evaluation. So I hope we will get more breakdown of the overhead, and we will be able to improve performance by tuning. So finally, summary and next steps. As a summary of today's talk, SPDK NVMe TCP target provides diff insert and strip feature without specialized hardware in SPDK 19.07, and the performance evaluation showed that the overhead are about 20% both read and write. And some of the next steps is, the first one is now Mellanox team is doing great work, and we will add the new feature, so that is we will support diff insert and strip feature also for RDMA transport in the next version, so that is SPDK 19.10. And as Gia said, SPDK master branch get the FC transport code recently, so I hope we can support diff insert and strip feature also for fiber channel transport soon. And I could get better feeling about the performance of user space TCP/IP stack. So so Jim mentioned about this in his opening session, and so I want to have more official performance data with vector packet processing as a next step. And the third one is we want to increase the range of support to the other BJ modules. And the final one is the feature is one of the enterprise storage features. So I want to work on other enterprise storage features, for example, load balancing or failover. And another one is currently SPDK supports only level 0, but we want to support more higher level, right? So, that's all from me today. Thank you.